In this lecture, we continue our discussion on queuing models. In the previous lecture, we derived some expressions for the M1 infinity model, where this M stands for Poisson arrivals with lambda per hour. This M stands for exponential service with mu per hour. This is the number of servers, C equal to 1. This is infinite queue length, and this is infinite population. We also use the notation where Pn is the probability that at steady state there are n people in the system, and we derived P naught is equal to 1 minus rho, where rho is equal to lambda by mu. We also indicated that lambda by mu should be less than 1. So, rho should be less than 1, particularly when we have infinite queue length. Now, the most important equation that we derived is P naught is equal to 1 minus rho, and we also derived P n is equal to rho power n P naught, which is rho power n into 1 minus rho. We also derived expressions particularly for Ls is equal to rho by 1 minus rho, and we also said Ls is equal to Lq plus rho, and we also used Ws. We also used the other relationship where we have Ls equal to lambda Ws and Lq is equal to lambda Wq. Now, with all these equations, let us work out a numerical example to understand what is meant by each of these equations. So, let us look at a case where an example where say lambda is equal to 8 per hour and mu is equal to 9 per hour. So, this would give us rho is equal to 8 by 9, rho is lambda by mu, which is 8 by 9. Now, from this equation P naught is equal to 1 minus rho, which is 1 by 9, which is 0.111. Now, P naught equal to 0.111 tells us that there is a probability of 0.111 that there is no person in the system. So, P naught is the probability that at steady state there is no one in the system, and that is 0.111, or 11.1% of the times there is nobody in this system. So, when there is nobody in this system, it means that the server is free. So, the probability that the server is not free is 1 minus P naught. So, 1 minus P naught is equal to rho, which is equal to 8 by 9, which is equal to 0.888 or 0.889. Now, this is the probability that there is at least one person in the system, which means this is the probability that the server is not free, or the server is busy, or the server is utilized. So, probability that the server is utilized is in this example 1 minus P naught, which is 0.888. Now, let us try to find out. Now, what is the probability that there is no queue? So, there is no q, we will say what is the probability that there is no q. So, there is no q when there is no one in the system P naught, or there is one person in the system and that person is getting served. So, there is no q. So, P naught plus P 1 would tell us that there is no q. So, this is P naught is 0.111 plus P 1 is rho P naught, which is 0.111 into 1 plus 0.888, and this would give us 0.2098. So, for our example, probability that there is no q is 0.2098, which means about 21% of the times there will be no q. A person who comes joins the queue as the first person. Now, if it turns out that out of these 21% of the times, there could be some times when the server is free. So, the person who comes in will straight away go to the server and get the service, and there could be some times where a person who comes in joins as the first person in the queue and waits for service. Now, let us try to find out what is the probability that there are 10 people in the system. Probability that there are 10 people in the system is given by P 10, which is rho to the power 10 P naught, which is 0.888 to the power 10 into 0.111, and this will be given as 0.0341. So, this computation tells us that the probability that there are 10 people in the system is 0.0341, which means roughly 3.4% of the times there will be 10 person in the system, one person getting served and the remaining 9 waiting for service. Now, if we wish to find out probability, that there are at least 2 or more people in the system, which means probability of n greater than or equal to 2, probability that there are at least 2 or more people in the system will be equal to P 2 plus P 3 plus etc. plus P infinity. Now, this will be equal to 1 minus P naught minus P 1, because P naught plus P 1 plus P 2 plus etc. up to infinity is 1. We have already found out P naught plus P 1 is 0.2098. So, 1 minus 0.2098, this will be 0.2097. So, 0.7902, which means 79% of the times there will be 2 or more people in the system. So, this way we can find out the probabilities of estimating or finding out the probabilities that a given number are there in the system, more than a given number are there in the system, up to a given number are there in the system, and so on. So, this and also the server utilization. Server utilization is 1 minus P naught. Probability that there is no queue is this. Probability that there are exactly 10 is given here. Probability that there are at least 2 is given here. Like this, we can have our computations to find out the probabilities of so many number of people in this system. Now, for this expected number in the system, Ls is equal to rho by 1 minus rho, which is 8 by 9 divided by 1 minus 8 by 9, which is 8 by 9 divided by 1 by 9, which is equal to 8. Now, expected number in the system is 8, which means that when a person walks into this system, then on an average the person can expect 8 people in the system, 1 person is getting served and the remaining 7 are waiting in this system. Now, LQ is equal to LS minus rho, which is 8 minus 8 by 9, which is 64, 72 minus 8, 64 by 9, 9 7s are 63, 7.11. So, expected number of people in the queue is 7.111 in this. Now, we can also find out Ws and Wq. Ws is equal to Ls by lambda, which is 8 divided by 8, which is 1 hour. So, a person that comes into this system will require to wait for about 1 hour both in the queue and to get the service and then leave the system. So, expected waiting time in the system is 1 hour, and Wq is expected waiting time in the queue is Lq by lambda, which will be 7.111 by 8. This is 0.88 are 64, 71, 8 are 64, 0.888 hour, which is approximately 53 minutes. The person would have to wait on an average for about 53 minutes before the person gets his or her turn for service, and then there is a service time and then the person comes out of this system. We also need to understand a little bit more about this Ls, Lq, Ws and Wq. Now, the Ls, Lq, Ws and Wq are all expected values. Ls is the expected length of the system, which means the expected number of people who will be there in the system, which happens to be 8. Now, it does not mean that every time a person comes in, the person will see exactly 8 people. So, it does not hold for a particular instance. There could be times when you come and join this line, there can be about 3 people, there could be times there can be about 10 people or 12 people and so on. But if you keep on computing the number of people who are there in the system and then average it out, the average will come to 8. So, that is what this actually means. This does not say that for every person who comes in, the person has to wait for 1 hour in the system or 53 minutes in the queue. There could be instances where it is less, there could be instances where it is more, but on an average this will be 1 hour in the system and 53 minutes in the queue. So, we have to understand that these are only expected values, and as more and more people come in, if we take the individual values and average them out, we will get these kind of numbers 8, 7.11, 53 minutes, 1 hour and so on. Now, obviously we can do this the moment different values of lambda and mu are given, or even if it is enough to give rho, one can compute all this. So, we know the equations for Pn, we know the equations for Ls, Lq, Ws and Wq. These are the expected outputs which are normally looked at. These are outputs or these are parameters which are of importance from a customer viewpoint. These are internal equations that relate the input, that is rho, to the probabilities, and using this rho we can get expressions for each one of them. Now, we move on to the second model. The second model is called MM1 n infinity model, which means that the queue length now is not infinite, but the queue length is finite. So, it becomes a finite queue length model. So, it becomes a finite queue length model. So, some of those equations will still hold, except that when we have n plus 1 people in the system, or if we have n people in the system, the person who is coming in does not join the line and leaves. So, whenever a person comes in, the person can see either 0 or 1 or 2 up to n, and the person does not see the n plus 1. So, the system will not have more than capital N number of people. So, the probabilities will now become P naught, P 1 up to P n, where capital N is the maximum number that this system will hold. So, the one of the equations will change, that we will have P naught plus P 1 plus P 2 as etcetera plus P n will be equal to 1. Now, we know the relationship between these. So, this is P naught plus rho P naught plus rho square P naught etcetera plus rho power n P naught is equal to 1. Now, if we take P naught outside into 1 plus rho square plus rho power n is equal to 1. Now, if rho can, in this case rho can even be equal to 1 or greater than 1, because we have this forced bulking that actually happens. So, this is a finite geometric progression that has n plus 1 terms, with the first term equal to 1 and the common ratio being equal to rho. So, P naught into the summation of this will be 1 minus rho to the power n plus 1 by 1 minus rho is equal to 1, from which P naught is equal to 1 minus rho by 1 minus rho to the power n plus 1. So, the equation or the expression for P naught changes. Earlier it was only 1 minus rho, now it is 1 minus rho divided by 1 minus rho to the power n plus 1. So, the moment the expression for P naught changes, expression for a general P n is equal to rho to the power n P naught up to n equal to n, or up to n is equal to 1 to n, for n is equal to 1 to n. We can use this to find out the probabilities that there are small n number of people in this system. The rest of the equations are quite similar and we derive them. We need to derive the expression for Ls, Lq, Ws and Wq. Now, let us derive this expression for Ls. Now, Ls is the expected number of people in the system. So, it is an expected value from 0 to capital N, because we may have 0 people in the system, 1, 2 etcetera up to capital N. So, this will be like 0 into P0 plus 1 into P1 plus 2 into P2, it is a normal expected value. So, we write the expression here. So, this is sigma n equal to 0 to n rho power n P naught. So, now we take P naught outside and a rho outside. So, P naught into rho sigma n equal to 0 to n rho power n minus 1. Now, this is P naught into rho into sigma d by d rho of rho to the power n. So, this will be P naught into rho, and as usual we switch the differentiation and the summation to get d by d rho sigma rho power n So, this will be P naught into rho into d by d rho of rho power n. So, this will be d by d rho of rho power n is 1 minus so d by d rho of rho power n. So, this is summation up to n equal to 0 to n. So, this is 1 minus rho to the power n plus 1 by 1 minus rho. So, now this has to be differentiated to get P naught rho into this is 1 minus rho the whole square. We use the formula d by d rho of u by v is v du minus u dv by v square. So, we have 1 minus rho the whole square. So, this is 1 minus rho into differentiation of this, which is v du. So, this is minus n plus 1 rho to the power n with a minus sign. This comes because this will give us 0, the minus will stay here, rho power n plus 1 would give us n plus 1 rho power n minus u dv, which is 1 minus rho to the power n plus 1 into differentiation of this, which is minus 1. So, this will become a plus by this. Now, this one is further expanded to Ls is equal to P naught rho by 1 minus rho the whole square into 1 minus rho to the power n plus 1 plus n plus 1 rho to the power n into 1 minus rho. This will become P naught rho by 1 minus rho square into 1 minus rho to the power n plus 1 minus n plus 1 rho to the power n plus 1. Now, what I am doing is I am multiplying this n plus 1 into rho to the power n into minus rho will give me minus n plus 1 rho to the power n plus 1. Now, I am multiplying the other one. So, plus n plus 1 rho to the power n. This on further simplification will give me P naught rho by 1 minus rho square 1 minus. Now, this is minus rho to the power n plus 1. So, when I expand this I get this is n plus 1 rho to the power n so plus n plus 1 rho to the power n, and what do I get here? The minus of n plus 1 rho to the power. So, this when I differentiate I get v square v du 1 minus rho into n plus 1 rho to the power n with a minus sign plus u dv 1 minus rho to the power n plus 1 into minus 1. So, I get plus 1 minus rho to the power n plus 1. So, I write this as 1 minus rho to the power n plus 1, 1 minus rho to the power n plus 1 minus n plus 1 rho to the power n 1 minus rho. I am writing this term first. So, 1 minus rho to the power n plus 1 and I am writing this term later. So, I get minus 1 minus rho n plus 1 rho to the power n. So, this will become 1 minus rho to the power n plus 1. Now, I am expanding this. So, there is a minus sign here, n plus 1 rho to the power n into minus rho will become n plus 1 rho to the power n plus 1 with a plus sign here. This one will become minus n plus 1 rho to the power n. So, further I get this is minus rho to the power n plus 1 plus n plus 1 rho to the power n plus 1. So, when I expand this, I will get this term will become, there is a minus rho to the power n plus 1, there is a plus rho to the power n plus 1 which will get cancelled. So, I get plus n rho to the power n plus 1 minus n plus 1 rho to the power n is what I get. Now, I expand this P naught. Now, this P naught is 1 minus rho by 1 minus rho to the power n plus 1 and I have a 1 minus rho square already. So, this into 1 plus n rho to the power n plus 1 minus n plus 1 rho to the power n. Now, again one of these will get cancelled here with this will go, this will remain. So, from which I get the expression Ls is equal to I have a rho also here. So, I have rho by 1 minus rho into 1 minus rho to the power n plus 1 into 1 plus n rho to the power n plus 1 minus n plus 1 rho to the power n. So, we get an expression like this for Ls when we put a limit on this n. So, the expression gets a little more complicated. Earlier it was only rho by 1 minus rho. Now, we are multiplying this by a term which is like this 1 plus n rho to the power n plus 1 minus n plus 1 rho to the power n by 1 minus rho to the power n plus 1. Now, this term we multiply with the older one. Similarly, P naught was 1 minus rho. Now, P naught has become 1 minus rho divided by 1 minus rho to the power n plus 1. So, this 1 minus rho to the power n plus 1 keeps coming because we have a restriction on this n. So, once we know Ls, we can get the other expressions which we need to get expressions for LQ, Ws and Wq. Now, there is a slight difference in these relationships and that happens like this. Earlier we had Ls is equal to Lq plus lambda by mu. Now, we have something called lambda effective is equal to lambda into 1 minus Pn. Now, what is this lambda effective? Now, because we have a finite restriction on the Q length, we are going through what is called a forced balking. For example, if a customer comes and the customer finds that there are already n people in the system, then the person balks, which means everyone who is coming in does not join the line. So, some people leave. So, the actual arrival rate, even though it is lambda, not all lambda come in, there is an effective rate, because the moment we have n people in the system with a probability p n, people leave the system. So, people who actually enter the system, now they have a probability of 1 minus p n. So, the effective arrival rate is lambda into 1 minus p n, which is actually less than lambda. The moment we have this lambda f, then we write Ls equal to Lq plus lambda effective by mu. Then we have the usual relationships, Ws is equal to lambda Ls and Wq is equal to lambda Lq. I am sorry, other way, Ls is equal to lambda Ws, Ls is equal to lambda Ws, Lq is equal to lambda Wq. So, we have these equations, Ls is equal to lambda Ws and Lq is equal to lambda Wq. Now, this is in hours, this is people per hour. So, the multiplication would give expected number of people in the system. So, these are the governing equations when we look at a MM1 n infinity model. Now, the expression for P naught changes, P naught now becomes 1 minus rho by 1 minus rho to the power n plus 1. Now, the expression for Ls changes to rho by 1 minus rho into this expression 1 plus n rho power n plus 1 minus n plus 1 rho to the power n by 1 minus rho to the power n plus 1. And then we also have an effective lambda, because some people leave the system, and then the Ls, Lq, Ws, Wq are now based on the effective lambda. Now, what we will do now is we will take a numerical example to understand what happens when we put a capital N into this system. Now, in order to do that, let us now, if in the same previous example, let us say we have lambda equal to 8 per hour, mu equal to 9 per hour, and we restrict say n is equal to 10, which means when the system has 10 people, the 11th person who comes in does not join the system. So, rho is equal to 8 by 9. Now, P naught, which was earlier 1 minus rho, now P naught will become 1 minus rho by 1 minus rho to the power n plus 1, which is 1 minus 8 by 9 divided by 1 minus 8 by 9 to the power 11, and this on simplification would give us now the probability that there are 0 people in the system is given by 1 minus rho by 1 minus rho to the power n plus 1. So, n is equal to 10. So, n plus 1 becomes 11, and this on computation gives 0.1529. So, this means that about 15% of the times this system will have 0 people in the system, or 15% of the times the server will be unutilized or idle. If we compare with what happened to P naught in the earlier model, where this n was infinity, P naught was 1 minus rho. So, 1 minus rho was 1 by 9, which is 0.1111, which means about 11.1% of the times the server was free. Now, 15% of the times the server is free. Now, when we restricted this n equal to 10 from n equal to infinity, now it is not very good from the system point of view, in the sense that the server is idle for more times in this model than in the earlier model. Later we will have to see that this is beneficial from a customer point of view, because the corresponding Ls and Ws will come down. So, now when we have P naught equal to 0.1529, and if we try to now find out what is the probability that there is no Q, it means there is no Q when we have either 0 people in the system or 1 person in the system. So, P 1 is equal to rho P naught, which is 8 by 9 into 0.1529, and this is 0.1359. So, probability of no Q is P naught plus P 1, which becomes 0.2888. So, about 28% of the times there will be no Q, and a person who comes will either directly go to the server if the server is free, or if one person is being engaged, this person will come in as the first person waiting. Now, in the earlier model, the probability that there was no Q when had a probability of 0.2098. So, about 20% of the times there was no Q, here 28% of the times there is no Q. So, this is kind of beneficial from a user point of view, that when the person comes in, there is a higher probability that there is no Q. There is a higher probability that the server is idle, which means the person can easily get to the server with a higher probability. Now, continuing, probability that there are 10 people in the system, P 10 is rho power 10 P naught, this will be 8 by 9 to the power 10 into 0.1529. This on simplification would give us 0.0471. So, probability that there are 10 people in the system is 0.0471, and in the earlier example, probability that 10 people in the system was 0.0341. Now, this P 10 is extremely important from this point of view, because now from P 10 we are going to say that what is the probability that a person who comes into the system does not join the system. So, the person who comes into the system does not join the system when there are 10 people in the system. So, probability that someone does not join the system is 0.0471. So, probability that a person coming in joins the system is 1 minus 0.0471, which is 0.9529 is the probability that somebody comes into the system. So, the effective arrival rate lambda e will be lambda into 0.9529, which will be less than 8. Now, continuing, expected number in the system Ls is given by this formula. Now, substituting the values here, rho is equal to 8 by 9, capital N is equal to 10, so that n plus 1 is 11. So, we can do this computation to get Ls on computation would give us 3.856. So, number of people in the system now is 3.856, and in the earlier example we had Ls equal to 8. The expected number in the system in the earlier model when n is infinity was 8. Now, with lot of people leaving the system, now Ls, the expected number of people in the system, now comes down to 3.856 when we put a restriction that a maximum of 10 people will be there in this system. Now, again we can calculate the rest of them. Now, Ws is equal to Ls by lambda effective lambda e, and this will be 3.856 divided by 7.6233. Now, this 7.6233 is nothing but 0.9529 into 8, because 0.9529 is the probability that a person comes in. So, the expected arrival rate is 8, which is lambda, into 0.9529, which becomes 7.6233. Now, this will become 0.5058, which is the waiting time in the system, which was earlier 1 hour, has now come down to half an hour, because we put this restriction. Now, the last one to compute is WQ. WQ is equal to Ws minus 1 by mu, which will become 23.68 minutes after the substitution. Earlier it was about 53 minutes when we used n equal to infinity. So, this is how we work out all these numbers. The important learning from these is that when we put a restriction on this capital N, so P naught will increase, which means the probability that 0 people in the system will go up, which means the system utilization or the server utilization will come down. Now, this is not a very healthy thing from a system point of view, because the system would like to have its server utilized as much as possible. But from a customer or a consumer point of view, you realize that probability that a certain number of people are there in the system is actually increasing. So, the arrival person is happy about it. Now, in this, only 95% of the people who actually come into the system join the queue. The expected number in the system comes down drastically, expected time in the system comes down drastically. So, from a customer or a consumer point of view, this N is useful, because you may come in, and when you come in, this is the performance. But the customer also has to be aware that there is a chance, or about close to 5%, that a person coming in is not able to join the line, which again is something that the system has to worry about. Now, those who join the system are very happy, because the waiting times and the expected number has come down, but obviously we will lose about 5% of the business, because 5% of the customers do not come and join the line. So, the n equal to 10 or the finite queue length model has these characteristics. From a system point of view, the utilization is coming down, because not all the people are joining. So, the system has to worry about the fact that about 5% in this case do not join. From the point of view of the customer, we have a set of customers who do forced balking. So, they may not come back into the system again, they may choose not to, or those who come in are very happy, because their performance measures have come down drastically. Now, we look at the third queuing model. Third model is MMC infinity model, which is a multiple server model. So, we have more than one server. We again look at the Poisson arrival and exponential service. We have more than one server, we have infinite queue length. So, everybody who comes in will join the line. If we look at the case of, say, 2 servers, we may say that there is a common line and people join this line, and depending on which server is free, they will go to that server. We also assume that the service rate mu per hour is the same irrespective of the server. So, in this case, we should actually look at lambda by C mu, because mu is the service rate of one server. Since there are C servers, C mu is the effective service rate, lambda is the effective arrival rate. So, in this case, lambda by C mu will have to be less than 1, because we already said that in some form lambda by mu has to be less than 1. Now, it is lambda by C mu will have to be less than 1, or rho by C has to be less than 1. Now, let us look at some steady state derivations for this kind of a queuing system. Now, in this type of a queuing system, we can assume that lambda n is equal to lambda, irrespective of the number of people in the system, the arrival rate is only lambda, but mu n is equal to n mu when we have n less than c, and it is equal to c mu when n is greater than or equal to c. Now, what do these equations tell us? If let us assume that there are 4 servers here, so there are 4 servers. If we have 4 or more people in the system, the service rate is 4 times mu, because all the servers are busy. So, the service rate will be 4 times mu or c mu when n, the number in the system, is greater than or equal to 4, which is what is given here. Now, the effective service rate, if we have only 2 people in this is the queue. So, if we have only 2 people in the system, there is a person here, there is a person here, the other 2 people are idle. So, the effective service rate is only 2 mu. So, it is equal to n mu if n is less than c, and it is equal to c mu when n is greater than or equal to c. Now, with this, we also observe that in this model, every person who comes will join the line. So, we will have P naught, P1, P2 up to P infinity in this model. So, now we write the expression for a general Pn. Now, Pn has a general expression rho power n P naught, or a general expression lambda power n by mu power n P naught. This is the general expression for rho n, for Pn, n can go up to infinity. Now, we have to, because lambda changes or because mu changes depending on this n and c, this has to be rewritten. So, this will be rewritten as Pn is equal to, if we have number of people n less than c, we have lambda power n, which is the arrival rate. Now, mu to the power will be mu 2 mu up to n mu into P naught. Now, this comes because n is less than c. If you look at a case where c equal to 4 and say n equal to 3, then when I have one person in the system, I will have mu, 2 people is 2 mu, 3 people is 3 mu. So, you will have mu 2 mu up to n mu into P naught. So, this will become lambda by mu to the power n 1 by n factorial P naught, where n is less than c, and the same P n will be lambda power n by, if the number of people in the system is say 6 and c is 4, we will then have mu, 2 mu, 3 mu, 4 mu, and if we have 5 or 6 or 7, the service rate is always going to be 4 mu, 4 mu, and so on. So, this will become P n is equal to lambda power n by, this is 1 into 2 into 3 into 4, now c is 4. So, we have c factorial mu power n, and for the first 4 it will be c factorial, for the remaining n minus c it is c c c. So, c factorial into c to the power n minus c into P naught. So, P n will have now 2 distinct expressions, which is lambda by mu to the power n 1 by n factorial P naught, where n is less than c, and P n will be lambda by mu to the power n c factorial c to the power n minus c into p naught when n is greater than or equal to c. So, we have both these expressions which have to be used. Now, using these two expressions, we also have p naught plus p1 plus p2 plus up to p infinity is equal to 1. So, a general Pn will now be like this, which is rho power n p naught, because lambda by mu is rho. So, rho power n p naught by n factorial, this is sigma n equal to 0 to c minus 1, because this is applicable for n less than c. So, n equal to 0 to c minus 1, this is applicable for n less than c. So, n equal to 0 to c minus 1 rho power n by n factorial p naught plus sigma n equal to c to infinity rho power n by c factorial c to the power n minus c p naught is equal to 1. Now, this will become p naught can be taken out. So, p naught into rho power n by so this n is equal to c minus 1 rho power n by n factorial. So, this term will become 0 to c minus 1. So, rho power n by n factorial. So, what I will do now is I will write it as p naught into sigma 0 to c minus 1 rho power n by n factorial plus this is expanded now. So, rho power n by rho power n p naught c factorial. Now, this rho power n is expanded as rho power c rho power n minus c by c power n minus c. So, we have sigma n equal to c to infinity is equal to 1. So, this will become p naught into sigma 0 to c minus 1 rho power n by n factorial plus expanding this will give us rho power c by c factorial into p naught is taken outside. So, we do not have to write p naught again here, p naught has been taken outside. So, rho power c by c factorial into, now this is when n is equal to c, this is n minus c. So, when n is equal to c, because n minus c comes as, this is rho power n is written as rho power c into rho power n minus c. So, when n is equal to c, this term is 1. When n is equal to c plus 1, this term is rho by c plus rho by c the whole square up to infinity is equal to 1. Now, this is an infinite geometric series with first term as 1, the common ratio r as rho by c, and we also know that rho by c will have to be less than 1. We mentioned here that rho by c or lambda by c mu should be less than 1. Therefore, we can use the summation formula for the infinite geometric series to get p naught into sigma 0 to c minus 1 rho power n by n factorial plus rho power c by c factorial. Now, this is a by 1 minus r. So, 1 by 1 minus rho by c is equal to 1, from which we can write the expression for P naught. So, we can write the expression for P naught as, so now P naught is equal to 1 by sigma 0 to c minus 1 rho power n by n factorial plus rho power c by c factorial to 1 minus rho by c. Now, this is the expression for P naught. Now, having derived this expression for P naught, now P n can be written as, if n is less than c, then we can use this expression as rho power n by n factorial P naught when n is less than c, and when n is greater than or equal to c, then P n will become rho power n by c factorial c to the power n minus c into P naught. P naught, for P naught we can use this expression. So, once we know the expressions for P naught and in general for a P n, the other thing that we have to do is to calculate Ls, Lq, Ws and Wq using these expressions. Now, the computation of Ls, Lq, Ws, Wq we will address in the next lecture.